Howdy. I want to share two. One is an article, one is from Wikipedia. Two things, they are related, probably in many ways and forms. This is, at least for me, in a way, rather complicated stuff. There are many funny words, stuff there, you will probably figure out. So let's have a quick read in, because it's not going to be a read through. Nature Communications, 3rd November this year. Generating intense electric fields in 2D materials by dual ionic gating. I was really wondering first, 2D materials. That's in a way an oxymoron. Because even though if you would go down to the size of an atom, it would be spherical. It would be 3D. There's that's an interesting thing too. One of the things I was trying to wrap my head around, still trying, but since there is electric fields and ions and stuff, it just interests me because the electric force is, in a way, it seems to more and more coming into mainstream media as well, or mainstream science, or however you want to put it. Abstract. The application of an electric field through two-dimensional materials, 2Ds, modifies their properties. For example, a band gap opens in semi-metallic B-layer graphene, while the band gap shrinks in few-layer 2D semiconductors. The maximum electric field strength achievable in conventional devices is limited to less than -3 volts per nanometer by the dielectric breakdown of gate dielectrics. Here, we overcome this limit by suspending a 2dm between two volumes of ionic liquid with independently controlled potentials. The potential difference between the ILs falls across an ultra-thin layer consisting of the 2dm graphene, so it's just a hexagonal shape. One layer of graphene, probably iron, and the electrical double layers above and below it, producing an intense electric field larger than 4 volts per nanometer. This field is strong enough to close the band gap of few layer WSE2, thereby driving a semiconductor to metal transition. The ability to apply fields in order of magnitude higher than what is possible in dielectric gated devices grants access to previously inaccessible phenomena occurring in intense electric fields. Maybe these people who made this, they would be interested about the Sapphire project. Introduction. Electric fields are widely used to control material properties and to explore diverse physical phenomena. The first group of phenomena appears due to changes of the carrier density induced in a material by the field at its surface, typically explored using field effect transistors. Electric fields also cause a second, qualitatively different group of effects. It's a group of effects when the field penetrates through the material's bulk. We can just imagine this in a scale bigger, like Earth. Field penetrates through material's bulk. In this case, the presence of a field inside the material breaks symmetries, bends the band structure along the direction of the field, and modifies the energetics of excitants with a dipole moment parallel to the field. In conventional FETs, the The induced carriers at the material's surface almost completely screen the field in the bulk of the material. Therefore, a dual gate FEET with a pair of gate electrodes above and below the material under study is used to explore the effects of an external electric field penetrating a material. In this configuration, the field strength is all controlled by the potential difference between the bottom and top gates, while the Fermi level is determined by their sum. However, an important limitation for studying large electric fields in conventional solid-state FEETs is the breakdown of gate dielectrics happening around 0.3 volts per nanometer. Somewhat larger dielectric strengths, less than 1 volt per nanometer. Sorry if I misspelled this. I think it's volt per nanometers. Are measured using local probe techniques. Yeah, that's very interesting. And despite they are talking about 2D materials, intense electric fields, I think this has quite much to do with Earth as a electrical charged body in space as well, so it will affect or maybe explain some weather phenomena as well. But anyway, now let's go to something which is really fun to read. Chirality. Chirality? Don't know. Probably the article or paper I wrote it before made me googling chirality. In chemistry, a molecule or ion is called a chiral. Maybe it's chirality after all. If it cannot be superposed on its mirror image by any combination of rotation, translations, and some conformational changes. The geometric property is called chirality. The terms are derived from ancient Greek gyr, hand, which is the canonical example of an object with this property. Have you ever really looked at your hands? A chiral molecule or ion exists in two stereoisomers. I said that's fun to read. There are like so many words, and some repeat all the time again, all over again. In two stereoisomers that are mirror images of each other, called enantiomers. They are often distinguished as either right-handed or left-handed by their absolute configuration or some other criterion. The two enantiomers have the same chemical properties except when reacting with other chiral compounds. They also have the same physical properties except that they often have opposite optical activities. A homogeneous mixture of the two enantiomers in equal parts is said to be rachemic, and it usually differs chemically and physically from the pure enantiomers. Chiral molecules will usually have a stereogenic element from which chirality arises. The most common type of stereogenic element is a stereogenic center or stereocenter. In the case of organic compounds, the stereocenters most frequently take the form of a carbon atom, which might be very important since we are carbon beings. And as I was reading this, somehow I could not prevent myself noticing that I was thinking about DNA. You know, imagine this would be drawn like really cool. This is DNA. Chirality, which have a symbiose or something. Anyway. Yeah, because we are carbon beings. With four distinct groups attached to it in a tetrahedral geometry. And I have to admit, I'm not very sure, but I think the tetrahedron represents fire in the Platonic solids. So that's the flame in us. I don't know. A given stereocenter has two possible configurations which give rise to stereoisomers, diastereomers and enantiomers in molecules with one or more stereocenter. For a chiral molecule with one or more stereocenter, the enantiomer corresponds to the stereoisomer in which every stereocenter has the opposite configuration. Yeah, what a text. An organic compound with only one stereogenic carbon is always chiral. On the other hand, an organic compound with multiple stereogenic carbons is typically, but not always, chiral. In particular, if the stereocenters are configured in such a way that the molecule has an internal plane of symmetry, then the molecule is achiral and is known as a mesocompound. Of course. What else? Less commonly, other atoms like NPS and silica. Nitrogen, I don't know what P is. Probably I know, but I would have to check them out. But I think silica is Si. Maybe I want to figure it out once, but I don't share this with you because I want to know. Nitrogen, I don't know. Can also serve as stereocenters, provided they have four distinct substituents, including ion pair electrons, attached to them. So there is like this Birkeland current where we have silica in the center and stuff. I won't search it for now, but molecules with chirality arising from one or more stereocenters are classified as possessing central chirality. There are two other types of stereogenic elements that can give rise to chirality. A stereogenic axis, axial chirality. Is that a Birkeland current or DNA? I don't know. And stereogenic plane. And a stereogenic plane. Planar chirality. So here we have the 2D objects again. Maybe. Finally, the inherent curvature of a molecule can also give rise to chirality. Inherent chirality. So probably everything is a chirality. It's probably the most fundamental principle of all. I don't know. The types of chirality are far less common than central chirality. Binol is a typical example of an axially chiral molecule, while transcycloctene is commonly cited example of a planar chiral molecule. Finally, helicene possesses helical chirality, which is one type of the inherent chirality. This is as far as I went once reading, then I think I made a video, but I deleted it. Chirality is as important as an important concept for stereochemistry and biochemistry. Yeah, what is stereochemistry? I haven't heard of that, but maybe I click on it once. I haven't, you see it. Most substances relevant to biology are chiral. Yeah, we have to read that again. Most substances relevant to biology are chiral. What is it called? Fibonacci? Maybe? Such as carbohydrates, sugar, starch, and cellulose, the amino acids that are the building blocks of proteins, and the nucleic acids. Yeah, I think I wasn't that wrong earlier when I shared a thought about this. But anyway, in living organisms, one typical finds only one of the two enantiomers of a chiral compound. For that reason, organisms that consume a chiral compound usually can metabolize only one of its enantiomers. For the same reason, the two enantiomers of a chiral pharmaceutical usually have vastly different potencies or effects. Uh, Stereochemistry. The subdiscipline of chemistry involves the study of the relative spatial arrangement of atoms that form the structure of molecules and their manipulation. Ah. But somehow the word stereo is really confusing. It's also known as 3D chemistry. Finally, you can see, or what? Imagine the world 2D and then try to figure it out how it works in 3D, or what's the case here. I don't know, but I think I leave it here. I don't know if this was from any interest or listenable, but anyway, it's just a statement of me learning all the time. So I have proof for that I really try to learn about stuff. There's so many things to learn about. It's very interesting. But anyway, and all these things, they all, you can say they tie back to the White Rivers, mountain water, and peat, or whatsoever, plasma rocks, weather anomalies, Earth surface conductivity anomalies, so it reflects back to the weather, which reflects better back to the sun cycles. Solar activity can have huge influences on how people feel. You know, it's all one thing. Bits and pieces. I'm a hunter and gatherer. But anyway, stay interested. Thanks. Bye.